Thank you. Thank you for the organizer of the invitation. Today I will tell you more about details on how can we learn about the basic properties and structures of the accretion disks when the accretion rate is in the Super-Eddington regimes. This will be a little bit more theoretical and numerical, but I will try to connect what we can learn from the small scale studies on the implications to the growth of the supermassive black holes and the connection to the host galaxies. So just to start, a little bit of motivations why we want to consider the Super-Eddington accretion. Well, I think the first thing a lot of people ask is that we have observed the Super-Eddington luminosity for the stellar mass black holes in the local universe, for example, the ULX. So the naive question is that why it cannot happen for supermassive black holes? And also, it's very interesting that for the Eddington ratio, we typically observe for like quasars and AGNs, they're most actually the near or below the Eddington. So I think that still poses the question that what could happen for the regimes for the supermassive black holes. Another thing interesting that particularly relevant for this conference is that the Super-Eddington accretion can help grow the seed black holes quickly to the observed mass range of the early universe. And also, I think as I will show in the talk, when you have the accretion rate exceed the Super-Eddington exceed the Eddington limit, you also expect to produce very strong radiation as well as very strong outflow from the disk, which will have actually a pretty strong impact between the disk as well as the host galaxies. And we also heard a lot of talks on the TDEs yesterday. Theoretically, when you consider the disruption phase of the TDE, the estimated mass accretion rate is also expected to in the Super-Eddington regimes. So we also want to know what you expect to see in this case. So just to begin with, I think I just want to give us a definition on what I mean by Super-Eddington accretion. I think we all know there is a well-defined luminosity for the Eddington luminosity, which is simply if you take the spherical symmetric case and take the electron scattering opacity and make the radiation force balance the gravitational force, and you get the well-defined Eddington luminosity. But for the actual mass accretion rate in the disk, that is actually not well-defined. And the different people have different definitions. And in all this talk, what I will use in terms of mass accretion rate that you can have in the disk, which is essentially relevant to how much mass you can fit to the black hole, is simply if you take the Eddington luminosity divided by c² times 10, which is simply imply that if the efficiency is 10%, this Eddington accretion rate will give you the Eddington luminosity. So the simple Eddington luminosity, of course, is defined in the spherical symmetric case, but whenever you have some angular momentum for the gas accrete to the black hole, you also expect some kind of disk will be formed. And that's the whole reason that we want to study in this disk structure, what you expect in this case. Before we talk about all the simulations, I think it's good to remind us about the classic pictures that we all learned from the 1980s on the basically the slim disk model people have used widely to try to describe the disk in these regimes. In the basic accretion disk theory, when you think the accretion rate is above the Eddington limit, the accretion disk is expected to be optical thick with optical depths much larger than 1. And also the disk is also geometric thick with like scale height, the ratio between scale height and the radius to be larger than like 10% or so. A key idea in the classical picture of the Super-Eddington accretion is that because the optical depth is very large, so the photon diffusion time scale is very long, and the disk is relatively thick. So you have very rapid radial advection. So in this picture, most of the photons is thought to be advected to the black holes. And you roughly have about the Eddington luminosity that is able to escape from the surface of the disk. So that is a classical picture. But even in this classical picture, we also believe that some sort of outflow is also expected, because at least you will have one Eddington luminosity coming from the disk. However, since it has been like more than 25 years after the classical picture, and we know more about the details of the turbulence that we expect in the disk, and we should actually know better on the physical process that is happening in the disk. And some of the key questions that I will try to answer is there any other energy transport mechanism that in the disk that besides the simple photon diffusion? For example, we all know that if you like take the energy to the stars, if the luminosity is high, in some cases, you also expect the convection to happen. And the convection is also another efficient approach to transport the photon out of the disk. And that will have a direct impact in terms of total luminosity you expect from the disk, and will also change the disk thickness and how strong the disk is expected to beam the photons. And also, since we have much better tools to study the 3D structure of the disk, we also want to know how the luminosity and outflow properties change with the accretion rate. And more important, we actually want to know the conditions of the photosphere when you have the Super-Eddington accretion rate, so that we know what you expect to see when you have this kind of accretion going on. Before I go to the work that I have done, I should mention that there are already several groups in the past few years to study this kind of accretion disk in what different parameter space. I just list a few groups here. Some of them are focused on the stellar mass black hole regime. Some of them are 2D. I will not go to all the details of all those work. For the simulation that I will mention, they are particularly focused on the Super-Eddington accretion to the supermassive black holes, which actually have different properties compared with the accretion to the stellar mass black holes. So since I will talk about the small scale simulations, I just want to give you an idea of what we typically need in order to set up those simulations and what we can learn from them. Actually, one big question is when we do the small scale simulation, that because those simulations are so expensive, we can really only focus on the one in the region where you expect most of the photons are generated. And that also means that we actually do not know how the galaxy will fit the gas to the small scales. Unlike the stellar mass black holes, you can imagine, for example, if you have a binary system, you may have Rashidov overflow to fit the mass to the disk. But for the galaxies, it's really, I think, an open question how the gas get to the small scale from large scale galactic properties. And that basically, put another way to say that basically we do not really know what is the initial condition we should use for those simulations. And whether you have like circularized material or you have more spherical symmetric conditions that could change the property of the disk. But for those simulations, we just simply start with torus, as I showed in the movie. Basically, we put the torus very far away from the central region, and then we also put the weak magnetic field to start with. It's simply because nowadays we believe that the magnetorotational instability is a physical mechanism for angular momentum transfer, so that mass can accrete toward the center. So we just put the city magnetic field, and the MRI will develop, and the turbulence will cause the angular momentum transfer and the material flow to the center. Another key ingredient for those simulations that we actually need to solve the radiation transport equations so consistently and accurately with the gas together. And that's because in the super-Eddington regimes, you do expect the radiation force to play an important role to support the disk. And radiation force is the force to drive outflow. And more important, you can only get the properties of force field sub-consistently if you actually solve the transport equation directly. So the movie that I just showed, I can play it again, is basically the left panel is showing the 3D structure. We go from the initial torus and go to fully turbulent state, and the material accrete to the center, and we can study the property of the disk after it reaches roughly steady state. And the right panel, I'm just showing the vertical cut through the disk and showing the mass density toward the black hole, as well as flow velocity at the streamlines. So we have performed the simulations with different accretion rate towards the black hole. And the two simulations I show on this slide, the right panel have accretion rate, the mass accretion rate, 25 of the Eddington mass accretion rate. And the right panel has the mass accretion rate 52 times mass accretion rate, so that we can actually compare what the structure of the disk will change with different accretion rate. And the right panel just show one snapshot of the 3D structure of the radiation energy density, show how the gas is actually flowing toward the black hole. And the horizontal average structure is shown here. And the color is showing the mass density, and the streamlines again showing the flow velocity. So the typical structure that you expect in those disks is you have a disk which is indeed relatively thick. You accrete toward the black hole, and then most of the photons leave from the surface of the disk, which also carry a strong outflow. With the velocity, as you indicated by the color of the streamlines, typical velocity is around 0.1 to 0.4 speed of light. You come from those regions. So the simulation, the result can also be checked if you simply estimate what the velocity you expect, because the long-term radius for those outflow is around like 10 gravitational radii from those what in the region. And the typical terminal speed of the outflow is roughly the order of the escape, the comparing speed from the long-term radius. And that is basically consistent with the 0.1, 0.4 speed of light that we get from the outflow. There's the black dashed line in the plot for the two runs, which indicate the location where the optical depth is 1 when you integrate toward the rotation axis. And also, basically, it shows that when the accretion rate is increased, you will tend to push the photosphere closer to the rotation axis. In other words, the final region where you expect some kind of optical thin-ish part getting smaller when the accretion rate is increased. Another thing from those simulations that the small scales tell you the detailed structure disk, but you can also actually look go back to a little bit larger, say go to 800 or 1,000 gravitational radii and look at the radiation flux of the streamline. Basically, and what you see that once the disk escape, when the photons escape from the disk through the final regions, and then you will tend to escape to the basically the infinity, but with the opening angle not very strong beams. So this is definitely different from the classical picture. For example, people propose for UX that you only require the strong beaming to get the super-Eddington luminosity, which is actually not the case. So just to summarize for those two runs, the outflow is launched about 10 gravitational radii. And from the simulations, you can actually calculate the total radiative luminosity from the two runs, and the radiative efficiency is about 5 to 7% for the case. And the outflow also carry a very large mass flux with it. The net mass flux with outflow is about 15 to 50% of the net mass accretion rate that you have through the disk. And there's also associated mechanical energy flux with outflow together. And for that, for those two longs, we find that is about 15 to 30% of the total radiative luminosity. So you can also ask question, what the disk will change if you keep increase the mass accretion rate. So this is another picture of the disk structure. If you increase the mass accretion rate to 150 of the Eddington mass accretion, okay, to 150 of the Eddington accretion rate. So one thing you notice that the disk has become thicker, the optical depth is actually increased, and the funnel get even smaller. Also, there's a big change in terms of where the outflow is launched. In this case, the outflow is the launching radius is pushed further away from the black hole, which is now about more like 60 to 70 gravitational radii. And the consequence of that is that the outflow velocity is now reduced to only a few percent of the speed of light. And the radiative efficiency is also reduced because this is actually closer to the classical regime where the photon from the inner region is simply advected toward the black hole because the optical depth now is too large for the photon to escape. Another big question that we can learn from those simulations is what actually you expect to see from this kind of accretion disk. And that's simply the question that where is the photosphere and what is the typical temperature around the photosphere? For example, I think we heard a lot from the previous talk in the past few days that typically in the when people expect and model the spectrum, if you have a disk in the super-Eddington regimes, you take the same disk model, or you take an analogy to the sub-Eddington accretion disk. We have learned a lot in the local universe, which might not be true. So this is the plot the gas temperature in one of the super-Eddington accretion disk case. The T0 here is about 2 times 10 to 5 K. So in the main disk, because the disk gas and radiation are summarized, so the temperature is only about a few times 10 to 5 K. In the final regions, when the density is lower, so summarization time scale is much longer, you do get the very high temperature gas. However, one key thing that remember that for all those super-Eddington accretion disks, you will have a very large outflow with very large optical depths that basically push the photosphere very far away to a few thousand photosphere radius, a few thousand gravitational radii, with the effective temperature only about a few times 10 to 4 K. In other words, although the hot gas that even you can generate near the black hole will be very hard to see because of the obscuration of the very optical thick outflow. This is basically very similar to the property of like the massive stars. When we generate very large outflow, you also basically with a very low effective temperature because of the outflow. And if you make an analogy, if you compare the property of the sub-Eddington accretion disk, in fact, the inner regions actually have very similar thermal properties. But of course, the sub-Eddington accretion disk does not have this very strong outflow. So you can actually see through those inner regions directly. That's why you can see the coronal X-rays and all the other wavelengths. But I do not expect that you should see that at least not with appropriate viewing angle for the super-Eddington accretion disks. Okay, so this I just put the summary here. I think super-Eddington accretion is definitely possible if you have a disk. So you can get the mass accretion rate much larger than the Eddington limit. And the disk can produce very strong outflow with a typical velocity of 0.1 or 0.4 C. And it will get smaller if the accretion rate gets even larger. The luminosity do exceed the Eddington luminosity. And one key thing I want to emphasize, the photosphere you expect from those disks is very large with a very low photosphere temperature. Thank you.